Hello, future houses. I hope you're doing good. I hope you're doing fine. Another day, another topic that we would be decoding. And the topic for today is how does a ship float? A big ship floats, but a small pebble sinks into the water. Archimedes principle. But before decoding this thing, let me quote you C.S. Lewis, who once said that hardship often come and make an ordinary person or prepares an ordinary person for an extraordinary fate. So remember, whenever some hard time comes into your life, just think that something extraordinary is coming or some extraordinary things are on their way for you. Okay, so let's start decoding what Archimedes principle is and how does this make a ship float, and also how in the ship engineering helps the ship to be afloat. So before we start decoding what Archimedes principle does, we need to be very clear of two things. One is the gross tonnage, one is the displacement. Many people have confusion in terms of what gross tonnage is and what displacement is. Gross tonnage is actually the usable space available on board ships for cargo, crew, passenger, which can be used. You can call it as ship's cargo carrying capacity. You can call it as ship's cargo carrying capacity. But whereas displacement is the actual weight of the ship. The actual weight of the ship is known as displacement. And why do we call it displacement? Because once a ship is placed into the water, it displaces certain amount of water. So because the ship displaces certain amount of water, that's why the weight of the ship is termed as displacement. You can read all these things. Whatever I've said, it's all written over here. Now comes the Archimedes principle. Let me quote the Archimedes principle. Archimedes principle says when a body is partially or completely immersed in a fluid, not water or anything, in a fluid, it displaces the weight of the water equivalent to the weight of the object. Okay, so if I placed my hand into water, so the amount of water my hand will displace will be equivalent to the weight of my hand. Okay, the weight of the water which will be displaced will be equal to the weight of my hand. So three things comes into play. One is the buoyancy force, Archimedes principle, and what are the floating conditions. Buoyancy force, like gravitation, what gravity does, it pulls us downwards, right? It pulls us downward. But in terms of when you are at sea or in water, there's additional force that is acting against the gravity upwards. That is the buoyant force. One is the gravitational force, one is the buoyant force. So buoyant force is generally nothing. It is the upward force, which also helps you to swim in water. Okay, if you know how to swim, you will have this upward force, that is the buoyancy, which actually helps people to swim and to ship to stay afloat. Next thing is the Archimedes principle. It is the core of physics for making a ship afloat. But before we start off, let me quote what Archimedes principle is. Archimedes principle is nothing but when a body is completely or partially immersed in a fluid can be anything, gas, water, oil, anything. When a body is partially or completely immersed in a fluid, it displaces certain amount of that particular fluid in which it is immersed, and the weight of that displaced fluid is equal to the weight of the object which has been immersed completely or fully or completely or partially. Okay, so if I take my hand and I put it into a water tub, it will displace certain amount of water which will be equivalent to the weight of the hand. Okay, it will displace a weight of water which will be equivalent to the weight of the water. So now three things are there. One is the buoyancy force, Archimedes principle, floating condition. I have told you about Archimedes rule. Buoyant force, there's one force that is pulling us down, that is gravity, but in water there's additional force, that is the buoyant force, which pushes us upward. Upward force, which is buoyancy. Upward force from water opposing the ship's weight. It is not just technically ship's weight, it could be any weight. Okay, and the last thing is, what is the floating condition? Simple. The amount of water ship displaces when it is placed into the water should be equivalent to the weight of the ship. Considering that if this is a ship and it is being placed into the water, it should displace water with equal to equal to the weight of the ship, then only will she float. Okay. Okay. Water displacement in action. Now comes the bit technical part. How does this work? Now the hull design matters. Loading changes draft. Equilibrium achieved. So what is this? Hull design matters. How does hull play an important role for ship to float? Now, what Archimedes said was that, or let's keep Archimedes aside, but let's focus on what is the floating condition. What floating condition does is says that to make an object float in water, or in water, it is considered water, the weight of the water it displaces, should be equivalent to the weight of the object, Now, to fulfill this, what the naval architects do, they make the hull broad and wide. Reason being, what is the reason behind this? So the broader the ship's hull is, the more weight it will displace. The broader the ship's hull is, the more water it will displace. So the weight of the water would increase automatically because of the shape of the hull. So what in return happens, that the weight which is displaced because of the shape of the hull will become equal to the weight of the ship. If you're getting what I'm trying to tell is, this. Like, this is the ship's hull. Okay, this is the ship's hull. So if it is streamlined, it will not displace enough water to counter the ship's weight, because the ships are not made of some paper or anything. It is made up of heavy steel. So to counter that, they need to spread the weight along the water. So that means they make this hull broad. So that because of the broad shape of the hull, it displaces more water. The broad hull will displace more water, because of which the water that is displaced will become equivalent to the weight of the ship. If you're getting what I'm trying to tell is that the broader my ship's hull is, the more water it will displace because of the surface area. The more water it will displace. Now the more water she displaces, the more weight will get displaced in return. Okay, the more weight will get displaced. So now that weight will become equivalent to the weight of the ship. You getting me? You getting what I'm trying to tell you? Now loading condition changes draft. This is very simple. That the more you load, I hope you understood why they make this ship's draft broad. It's generally because the more draft, the broader the ship's hull is. Okay, the broader the ship's hull is, okay, it will displace more water. So in return, more water means more weight is displaced. So it could be either that more weight is displaced as compared to the weight of the ship, or the water which is displaced equivalent to the weight of the ship. Okay. Now the thing is, equilibrium achieved is when the weight of the ship and the amount of water displaced is equal. Okay. Bathtub analogy, it's all that when you take this bathtub duct, you see, if you dip it into the water, it will displace more water. If you push harder, it will displace more water. Now measuring cargo by water level. Okay, how do you do that? How dock people know that what amount of cargo is been loaded? Now what it does, there is this, when the ship is entirely empty, they know the draft of the vessel. They know to what level will the water be. So now as and when they start, and they know the distances very well. So as and when they start loading, the ship will sink deeper and deeper and deeper and deeper, right? The ship will sink deeper and deeper and deeper and deeper. So with that principle, they find out how much cargo is on board ship. How dock waters know? When cargo is loaded, the ship's weight increases. Yes, so the ship's weight increases, it will go down, requiring more displacement to stay afloat. Okay, so the more she is loaded, the more water she'll displace. Okay, workers estimate cargo weight by observing draft change, how much deeper the ship sits compared to its usual water line. As I said, they'll observe how much she is sitting. So with this, the dock people know that how much of cargo is loaded, because they know the usual water line. When she is totally empty, they know when to load, what is the limit, what is the initial limit when she is totally empty, and with that they compare how much of and the current water line limit. With that they compare the cargo that is on board ship. More cargo, she'll go deeper and more water displaced. Okay, it is very common, very simple to understand. Why steel ships don't sink? Now this is a matter of density. Now the game comes to density. For any object to float on water, okay, if I take a stone, if I take a ball made up of not ball, let us take this bathtub duck. If I place a stone into the water, it will go down. But if I take a duck and then I place it on water, it will float, because the only reason the duck floats and the stone sinks is the density of stone is higher than the density of the water. But whereas the density of duck, the bathtub duck, is lesser than the density of water. If you get what I'm trying to tell. Likewise, you might wonder that the pebble is this small, but the ship, which is generally made of material, if we place in water like steel, it will go down. But once we make it into a ship, it will not go down. It does not go down, because the actual density of the ship is lesser than the density of water. The density of ship is lesser than the density of water. Why and how is it achieved? It is achieved because of the void spaces inside the ship. There are so many void space which helps us to achieve the density of the ship lesser than the density of the water. Okay, density is mass per unit volume. How much stuff is packed into the float rule. Objects float if less dense than the surrounding fluid. I said an object which will only float if it is less dense than the fluid outside. If we take a ship and we try to float, try this ship to float on vegetable oil, there are high chances that the ship would sink, because the density of the ship is higher than the density of these oil. And hollow design wings. I said steel and air voids overall density less than the water. Okay, as I said, this is achieved by the hollow density, the hollow void spaces inside ship structure. Now, Archimedes principle and ship stability. As I said, two things: gravity and buoyancy. These two play a very important role for a ship to be stable, because it is not just to ship to stay afloat, but it is also necessary that through harsh weather condition, our ship still stays afloat. This is where center of gravity and center of buoyancy would come into play. Okay. Now, for stable position, center of gravity is above and center of buoyancy is below. They are exerting force which is equivalent, and which in turn lets the ship to float. Tilting ship, when the ship tilts like this, if the ship tilts, if this is upright, the ship is upright, but now she'll tilt like this. If you can see, she'll tilt like this. So my diagram is not actually very right, but let's assume that she's tilted to one point. So this center of buoyancy will actually play an important role. Now what initially where center of buoyancy was exerted over here, this place, let us consider this place where initially center of buoyancy force was exerted. Now once the ship has gone this way, now the center of buoyancy will exert force over here. So now once the ship is like this and the center of buoyancy is exerting force over here, now what will happen? This will come upright. And now when this goes like this, now the center of buoyancy will exert force over here. So because of this, the ship stays upright. The water conditions changes everything. Now we live in a world where we have got different types of water like hot water, cold water, salt water, fresh water. With changes of water, this also plays an important role for the amount of depth the ship goes in. For example, if you might have seen the video of freshwater lines and dark water lines, you know that once a vessel goes from salt water to fresh water, it sinks more, and once it goes from fresh water to salt water, it sinks less because of the density differences. Now likewise, we have same issue like salt water, fresh water, regional differences like you have tropical fresh water, and then tropical water, west north WNA, that is the West North Atlantic waterline. So these are all the different regions the world is divided into, and once the ship goes into these regions, it will not the amount of sinkage that the vessel will experience will not be similar in each type of water because of the density of the water, right? So because of this problem, we got Plimsoll mark into play, Plimsoll mark and the load line into play, which helps us to determine in which particular area, if it is in tropical area, what is the safe loading depth, what is the safe loading limit in tropical area. If it is going into fresh water area, then we know which is the safe loading limit for fresh water for the vessel in fresh water. If you see Plimsoll marks, side markings indicate safe loading depth for different conditions. Okay, cold water, North Atlantic, warm tropical fresh water. So these lines generally tell us what is the safe limit for us to load in these particular type of water. Okay, it is not necessary the amount. It is not necessary that the amount of sinkage of vessel. Sinkage is generally the sinking of the vessel in deeper, deeper or less deep. That is sinkage. So the amount of sinkage that a vessel will experience in salt water it is not necessary that it would be similar in fresh water. Okay, that's why Plimsoll mark has come into play. Now designing secret. Okay, voids and compartment. As I said, the air filled compartment. All of these things help the vessel to be afloat and reduce the density to the surrounding waters. Okay, as I said, because of this air filled spaces, we have reduced overall density and size advantage. However large the vessel is, but because of its hollowness, the vessel stays afloat, unlike a stone, because the stone is not hollow, but the ship is hollow. Now this stability, more than just floating, as I said, it is very important not just to stay afloat, but also to make sure that the ship is stable because you know the sea is very rough and you don't have same type of weather conditions, good weather conditions around. So somewhere you might experience rough weather, somewhere you might experience calm weather. So things are not uniform. So because of that, we have different engineering techniques like the center of gravity, okay, which helps us to, which is generally a downward force, okay, center of buoyancy, the upward force. And generally what naval architects, what they do is they adjust the center of gravity and the center of buoyancy point for their convenience to make ship to float better. It is generally experienced in cruise lines. And then the hull design, the shape and the proportion affect rolling behavior and sea responses. It's very difficult to understand or very complicated, but it's generally these hulls are made in such a way that the phenomena that I told you, that if this goes down, the center of buoyancy will push it upward to this point. This goes down, it will push it upward like this. Scale does not change the physics. Now, initially in earlier when it was Greek era, Archimedes time, the ships usually used to weigh 45 tons. But now the weight of the ships has gone up to 100,000 tons. And the biggest ship, her name was Sea-wise Giant, her displacement was 670,000 tons. So all of these things, irrespective of size does not matter. Physics does not change with respect to the size it is going on. So the same buoyancy principle is applied to a smaller ship like this and to a bigger ship like this and the average size ship like this. So principles apply equal to toy boats and ocean giants, Archimedes principle, and scales are perfectly balanced. So these are some of the reasons this is why ships float. There are so many things, so many of principles are put into it to make ship float safely, and not just float but to sail with utmost proper stability. The good thing is the oceans are made up of salt water, or at least water. The day the water is being transformed into oil, all the ships would sink in that pool of oil around the ship. So I hope you understood how ship float. If you have any sort of confusion, do mention in the comment box. And now, the Merchant Navy Decoded fraternity has launched the Decoded package coordinated by Captain Arun Gupta, a 40 years of master mariner, 40 years of sailing, a master mariner, was coordinated this course for deck cadets who are doing BSc, and their company will be approaching their university for placement drive. So this package is your lifesaver. And for deck cadets who have completed their pre-C, may it be DNS cadets or BSc cadets, this package will help you to build your theoretical concept, because this package has onboard practical videos which would give you very good idea before getting on board ship. It is also for cadets who have done one ship and they need more technical information. This package is your lifesaver. For cadet, it is generally two aspects. One is the practical, one is the theoretical. The practical aspect you will get hold of when you are on board ship with time, and with the theoretical aspects, it is just the package and your basic knowledge. So this was all from this video. These are our social media handles. Do join us. All the PDF for this PPT will be shared in this Telegram channel. Do join us. And I hope you liked the video. I hope you understood what I was trying to explain, the Archimedes principle and why ships float. Till we meet next time. Thank you.